We talked about derivatives, and we talked about graphical representation of derivatives. What about second derivatives, or the derivatives of the derivatives? Those are just as easy as plotting the derivatives for the first graph. Alright, so we have here f of x, which is x squared. And then we look at f prime of x, which is 2x. So the f prime prime, or f double prime of x, which is the derivative of f prime of x, would just be 2, right? You just take the derivative of that. So it would just be a single horizontal line which has the value of 2. The best part of derivatives is that they're very predictable. So you can go on and taking the derivatives of each graph and it will work the same way. But derivatives also help us in telling us about the original graph. For example, the critical points is something that probably in pre-calculus you might be used to using Desmos or something to figure out where they are. Or you might be drawing the graphs themselves and then you see the minimum is at this point, and then you might go ahead and say that's our critical point, and then take a long time to figure out each and every critical point on that graph. But with derivatives, you don't need to do that anymore. So let me explain this, right? With derivatives, the moment you identify an x-intercept, that changes everything for the parent graph. For example, the derivative of f of x is 2x, right? Whenever f prime of x is less than 0, that means f of x is decreasing. If it's greater than 0, f of x is increasing. And whatever comes in between those two, when f prime of x is 0, that is your critical point. It could be a minimum or a maximum. If it's going from negative to positive, you know that f of x is going to have a minimum. You can see that right here. This is going from negative to positive. And this is decreasing all the way down to minimum. If it were the other way, it was slanted from positive to negative, then this would be concave down, and it would be having a maximum. Okay? But what about our second derivative? That, in fact, has the same relationship with your first derivative as the first derivative has with the parent function. So, if you can see here, it's positive all the way, right? That means this graph, f prime of x, should be increasing all the way, which is happening. Okay. Now, what about with the parent function, f of x? That, in fact, is even better, because it tells us if it's concave up or concave down. If it's positive, it's concave up, as you can see here. If it were negative, it would be facing the other way. And if it were negative, the f prime of x graph would also be slanting the other way, so everything will adjust for itself. If you fix one graph, all the other graphs fix automatically. So one last thing here to illustrate how derivatives work. Just a final, concrete filling that will explain everything. Let's take the derivative until the derivatives end up getting to 0. So, f of x is x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, plus x plus 1. So, the derivative of that would be 5x to the 4th, plus x to the 4x to the 3rd, plus 3x squared, plus 2x, plus 1, plus 0. So we can ignore the 0. Now if we do f prime prime of x, again we would do the same thing. 20x to the 3rd, plus 12x to the 2nd, plus 6x to the first plus 2. And then that would be 0. Notice how for each derivative, the degree goes down by 1. The third derivative would be 60x to the second plus 24x plus 6. Now the fourth derivative, we're not going to put 3 or 4 of those apostrophes, right? So we're going to write the notation like this. If you write the notation of that, that's comprehensive. That way, if it's 99th derivative, all we have to do is write 99 and not put those things 99 times. That would be a nightmare. So, and the fifth one would be 120. Okay. Let me tell you this too about it. How would I do it in the other notation I taught you? This would be basically d to the fifth y over dx to the fifth. That's how you represent the fifth derivative of something. This exponent represents the numerical value of the derivative, and we kind of showed how this works in the last video with parametrics and second derivatives, where I took the derivative notation and as well as the whole parametrics idea of multiplying the derivatives and how we go from the first derivative to the second derivative for something that does not have x as the input variable. So you should definitely check that out. But yeah, I mean, this is all that is to it for additional derivatives. Derivatives are really easy to understand. And I hope this video helped. And please come back and watch the next video, which we'll be talking about Rolle's theorem and all. So thanks for watching, and see you next time.